Welcome back to the Explainer. So today, we're diving straight into this wildly fascinating paradox in machine learning. We almost always assume that if we want smarter AI, we just need to feed it more data, right? Give it a bigger brain, build out a massively complex architecture. But what happens when an AI literally becomes a victim of its own complexity? Like, what happens when its internal dialogue gets so incredibly loud that it can't even hear the actual truth anymore? We're going to look at some breakthrough research today that reveals something pretty stunning. Sometimes, teaching an AI how to intentionally forget is exactly the thing that makes it profoundly smarter.
Okay, let's dive into this. Can an AI actually know too much for its own good? I mean, in our rush to build better tech, there's this massive temptation to just assume that stacking more and more layers onto a neural network is a guaranteed recipe for better predictions. More is more, obviously, right? Well, not exactly. A team of researchers put this exact assumption to the test, and they found that as you stack those computational layers higher and higher, the AI doesn't magically get wiser. Actually, scratch that. It starts to develop a massive structural blind spot.
To really grasp what's going on with this blind spot, we need to talk about deep echo state networks, or deep ESNs. If you're familiar with them, you know you can basically think of a deep ESN as a highly advanced AI time machine. They're incredibly good at taking messy, chaotic sequences over time, think forecasting surges in a massive industrial energy grid, and making sense of them. They do this using a hierarchical structure, kind of like a corporate ladder. Raw data comes in at the ground floor, and it gets passed up layer by layer, with each level analyzing the timeline at a different, higher scale of abstraction.
And this brilliantly illustrates exactly where that corporate ladder breaks down. If you track that blue dotted line going up, which represents redundancy, you see it just shoots completely off the charts as we move deeper into the AI's layers. This right here is the hidden cost of all that architectural depth. As data travels from layer 1 all the way up to layer 10, the network isn't just extracting brand new helpful information. Instead, it's accidentally copying and amplifying the exact same features over and over again. The researchers perfectly dubbed this the echo chamber effect. The AI is literally trapping itself in an echo chamber of its own design. To put it in human terms, just imagine you're in a high-stakes corporate brainstorming meeting. At first, you've got a few people pitching really unique, diverse ideas. Great. But then you add more and more middle managers to the room. And instead of bringing fresh perspectives, they all just start agreeing with each other. Eventually, you're stuck in a crowded room with 50 people shouting the exact same idea at the top of their lungs. The volume is completely deafening, but the actual amount of useful information, it's completely tanked. That's intralayer redundancy. The AI's internal dialogue just becomes completely, uselessly redundant.
So, what does this all mean? Well, this isn't just some theoretical glitch. It has disastrous consequences in the real world. When an AI is trapped in this echo chamber, its final readouts become incredibly unstable. Because everyone in our metaphorical crowded room is screaming the exact same thing, if even a tiny bit of unexpected noise or some weird fluctuation enters the data, the entire network just panics. It massively overreacts, it fails to generalize any actual patterns, and it completely loses all the advantages it was supposed to get from having that deep, complex architecture in the first place. So how on earth do we fix an AI that's essentially overthinking itself into a total panic? The answer is a technique called dropout. You can see it represented here with those half-filled circles. What the network is doing is intentionally and randomly turning off or masking certain neurons during its training phase. So instead of letting every single node talk all at once, the system deliberately mutes a fraction of them.
Going back to that crowded meeting room metaphor, Dropout is basically the boss walking into that echoing room and just randomly kicking half of those shouting, redundant managers right out the door. By silencing the crowd, the actual, genuinely good ideas can finally be heard clearly. And what's really amazing about this research is they showed this isn't just some random guessing game. Using Dropout in these DPSNs acts as a highly calculated regularizer. It breaks up the groupthink, but it entirely preserves the AI's high-level capacity to actually make predictions. But here's where the researchers made their massive, game-changing discovery. The big question wasn't just if Dropout works, but how it should be applied. They compared a couple of main strategies. First up is uniform dropout. This treats every single layer of the corporate ladder exactly the same, kicking out a flat percentage of neurons across the whole board. The alternative is inverse dropout. With this one, you barely mute anyone in the early, shallow layers, but as you go deeper into the network, right where we know that echo chamber effect gets the loudest, you aggressively increase the muting effect.
Now, what's really interesting about this slide is how clearly it crowns a winner. We can totally bypass the heavy math here and just look at the performance across different noise levels. As you introduce more and more chaos, moving towards the right side there, the inverse strategies just consistently, absolutely crush the standard methods. When the environment gets super noisy and unpredictable, just uniformly muting the network doesn't cut it. You have to specifically and aggressively target those deepest layers.
So the core aha moment of this whole paper boils down to 4 simple words: the deeper, the quieter. Because architectural depth naturally concentrates all that redundant noise. Muting the deepest neurons acts as this brilliant structural bias. You force the deepest, most complex parts of the AI to just be quiet, which stops the echo chamber from ever forming. And the result? You radically improve the AI's accuracy and resilience. It literally learns exactly what to ignore.
Let's move on and see how this builds in the real world, because obviously a theory is only as good as its actual application. The researchers unleashed their inverse dropout AI on some highly chaotic, really messy energy consumption data. What we're looking at is the actual real-world demand from huge manufacturing plants in South Korea. Look at those jagged peaks and valleys. I mean, this is absolutely not a clean, predictable sine wave. This is the very definition of nonlinear chaos, a situation where even a tiny miscalculation can cost millions and millions of dollars.
And just to make sure this solution was actually robust, they didn't just test it on one easy dataset and call it a day. No, they tested it across 10 completely different, heavy industrial factory environments. We're talking about forecasting the minute-by-minute energy demands of massive steel forges, cement kilns, paper mills, 10 wildly different environments, all pumping out this chaotic, noisy data that would usually send standard AI models into a total tailspin.
So what's the big takeaway for deep ESNs here? When they were outfitted with this inverse dropout strategy, this very targeted depth-based forgetting, the models vastly outperformed older standard AI systems. They were able to stare down the massive nonlinear chaos of a steel plant's energy grid, process it without panicking, and deliver incredibly smooth, accurate forecasts. By proving that you can structurally force an AI to ignore its own redundant noise without any crazy complex math, these researchers have handed us a wildly powerful new tool for stabilizing some of the most complex forecasting problems on the planet. It's just a fascinating look at how sometimes, subtraction really is the ultimate form of addition. We build these massively complex systems, only to realize that their absolute greatest strength is unlocked when we teach them how to mute the noise. Which leaves us with a final thought to ponder today. If the world's most advanced artificial intelligence actually becomes exponentially smarter and more stable simply by learning what to intentionally ignore, well, what could we achieve if we finally learned to tune out our own echo chambers? Thanks for joining me on this explainer. I'll catch you next time.